Today on AI Paper Podcasts, we are breaking down AMEM4Rec, leveraging cross-user similarity for memory evolution in Agentic LLM recommenders.
Yeah, this is a big one. It's by Min Duc Nguyen and the team over at Vin University.
And it really attacks what might be the single biggest weakness of large language models in recommender systems.
Which is collaborative filtering.
Right. So the headline here is that LLMs are obviously great at language, but they're terrible at understanding that implicit group behavior. You know, the whole people who bought X also bought Y signal.
Exactly, not without leaning on some external pre-trained model like late GCN.
So AMEM4Rec proposes this agentic framework that builds a global evolving memory pool.
It pulls out these abstract behavior patterns from one user, finds similar patterns from other users, and then evolves them into this kind of shared wisdom.
And the key is it works. They beat state-of-the-art baselines like AgentCF and LLM rank on the Amazon and Mine datasets.
And they especially crush it in those sparse cold start scenarios where you have almost no user history to go on.
It's really the first true end-to-end solution I've seen where the LLM learns that collaborative signal by itself.
Instead of just being told what it is.
Okay, let's back up and really dig into this.
Yeah.
I want to start with the problem itself because it feels a little counterintuitive.
Right.
I mean, we treat LLMs like they have the sum of all human knowledge. If I ask GPT-4 what RAM goes with a specific motherboard, it usually knows the answer.
Yeah.
So why do we say they're bad at collaborative filtering?
That is the million-dollar question. And you have to distinguish between semantic knowledge and behavioral patterns.
Okay.
So you buy a motherboard, the LLM knows semantically that a CPU is related. It's read the manuals, it knows the socket types. That's just content-based reasoning.
Right. It knows how the objects relate to each other in the real world.
But collaborative filtering is about how people relate to objects. For instance, maybe there's a weird trend where people who buy high-end motherboards also tend to buy a specific brand of energy drink.
Ah, I see. There's no semantic link between a motherboard and an energy drink.
None. The link is purely behavioral. It's a pattern in the data.
So the LLM is acting like an agent on an island. It looks at my profile, sees the motherboard, and recommends a CPU.
Exactly.
Doesn't see the million other users who are also buying that energy drink.
Precisely. In traditional Rexus, we solve this with things like matrix factorization or GNNs. We process the entire interaction history of all users to find those hidden connections.
But an LLM agent is usually just processing one user at a time. It's isolated. It misses the wisdom of the crowd.
It misses the crowd wisdom.
Now, I've seen other papers try to fix this. We've talked about models like ColorRec or ALNMRec before. Didn't they solve this?
They solved it by, well, cheating is a harsh word.
Okay, using a crutch.
They used a crutch. Those models run a traditional collaborative filtering algorithm first. They get a score from a pre-trained model, and then they just paste that score into the LLM's prompt.
So the prompt is basically saying, hey, LLM, the math model says this user probably likes item B, so, write a nice justification for it.
Pretty much. And it creates this hard dependency on that external model. AMEM4Rec is trying to do something much, much harder.
They want the agents themselves to observe the crowd's behavior.
And learn from it end to end without needing a separate CF model as a babysitter.
Okay, so this brings us to the architecture, the global evolving memory. This is a multi-agent system, so let's walk through the life of a data point.
Yeah.
I'm a user on Amazon. I click on 3 things. What happens next?
So the first step is the creation agent. It looks at your sequence of interactions using a sliding window. In the paper, they found a window of size 3 was optimal.
Let's use the example from the paper to keep it concrete.
Good idea. So a user buys Just Dance 4, a PS Vita Comfort Grip, and Sonic the Hedgehog 4, episodes 1 and 2.
Okay, clearly a gamer. A handheld or console gamer.
Right. Now, a standard system might just embed those titles,
right.
But the creation agent in AMEM4Rec generates 2 very specific text fields. First is the behavior explanation.
That's the why.
Yes. For this user, the agent writes something like, user consistently purchases video games and accessories, indicating strong interest in gaming entertainment. It's a semantics summary.
Okay, straightforward enough.
But here's the key part. It also generates a pattern description. This tries to capture the structure of the behavior. For our gamer, it writes, sequential acquisition of Sonic titles, followed by PlayStation accessories.
Why separate those two? I mean, shouldn't the explanation just cover the pattern?
Not really. The explanation captures the intent gaming. The pattern captures the flow game A, then game B, then accessory C, and that flow is where the collaborative signal is hiding.
I see. If you just say he likes games, you miss the specific purchasing order that might predict the next buy.
Exactly.
Okay, so we have this text, Sonic, then grip. What do we do with it?
We vectorize it using SentenceBERT and throw it into a global memory pool, but we don't just leave it there. This is where the cross-user part kicks in.
Right.
The system immediately queries the pool and asks, who else has a pattern like this?
It's looking for other gamers who bought Sonic and then bought grips.
It retrieves the top K most similar memories. They found K equals 5 was the sweet spot. Any more than that and you start pulling in noise.
Now, this is the part I want to drill into, because vector similarity can be tricky. Just because two vectors are close doesn't mean the behaviors are actually compatible for a recommendation.
For sure.
Right. I mean, I could have a vector for buying a hammer that's surprisingly close to buying a hatchet, but the user's intent might be totally different.
That is the danger of pure vector search. You get false positives. So, to solve this, AMEM4Rec introduces a dual validator mechanism.
Okay.
Think of it as having two bouncers at the door of a club.
All right. Bouncer number one. What's his job?
Bouncer number one is the similarity validator. This is just pure math. It uses soft thresholds on the cosine similarity score. They set a low threshold at 0.55 and a high one at 0.9.
So walk me through the logic. What happens if my new memory comes in with a score of, say, 0.4?
The system says 0.4 is below our 0.55 threshold. You're unique. It treats your memory as a totally novel pattern and just adds it to the pool.
It's a new kind of behavior.
Yep. And if you score a 0.95,
Too similar.
way too similar. The system says, we already know this. We have a dozen memories just like it. It marks it for an update, but doesn't create a new entry. It's basically redundant.
But it's that middle ground that's messy, right? The 0.55 to 0.9 range.
That's where the evolution happens. The system says, okay, this is similar to what we have, but it's different enough to be interesting. But before it allows an update, it calls bouncer number 2.
The semantic validator.
The semantic validator.
And this is another LLM agent.
Yes. And this is crucial. The first bouncer checks the geometry. Are the numbers close? The second bouncer checks the meaning. It actually reads the text of your memory and the text of the retrieved memory and asks, do these actually describe the same kind of user behavior?
Can you give me an example of where the math says yes, but the LLM would say no?
Let's go back to our gamer. Maybe the vector search pulls up a memory about someone buying Sonic electric toothbrushes?
Ah, Sonic the Hedgehog versus Sonic the brand of toothbrush.
Exactly. Semantically, in vector space, if your embedding model isn't perfect, those might sit close together because of the shared word Sonic.
The similarity validator would pass it.
It might. But the semantic validator reads the text, sees video game versus dental hygiene, and just kills the link.
It prevents the system from learning that people who play video games also want clean teeth. I mean, they might, but it's not a causal link you want in your recommender.
It prevents what's called concept drift. If you start merging those memories, your gamer cluster slowly morphs into a hygiene cluster, and then suddenly you're recommending floss to someone trying to buy Call of Duty.
Right. Okay, so the bouncers let us in.
Right.
We have a verified match. Now comes the evolution. This is the part that sounded the most sci-fi in the paper. We're not just stacking memories, we're rewriting them.
Yes. This is the truly agentic part. The system takes the memory from user A, our Sonic gamer, and the retrieved memory from user B, maybe they bought Mario and a similar grip.
Okay.
It then prompts an LLM to synthesize these into a single evolved memory.
So what does that new text even look like?
It becomes more general. So instead of saying user bought Sonic, it might rewrite it to something like, users interacting with platformer franchises demonstrate a high probability of purchasing handheld ergonomic accessories.
Wow, that's fascinating. It turns the raw data into an actual rule.
It creates an archetype, and this is exactly why it's so powerful for the cold start problem.
Because if I'm a new user and I buy just one platformer game,
The system can map you to this archetype immediately. It doesn't need to see your full history. It just needs to see that you fit the rule it's already learned.
so the memory pool isn't just a database of transactions.
No.
It's a database of behavioral rules that the agents have written for themselves.
Correct. And because it's text-based, the LLM can easily understand and apply it during the final ranking phase.
Let's talk about that. The ranking phase. Inference time. I'm the user, I'm browsing. How does the system use these archetypes to show me a product?
So the ranking agent gets 3 inputs. It gets your current user history, a list of candid items, say 20 of them, and the retrieved evolved memories that match your profile.
So it gets that rulebook we just talked about.
Exactly. And the prompt explicitly tells the LLM, rank these items. Use the user's history, but prioritize items that align with these collaborative insights.
It's basically whispering the answer in the LLM's ear. Hey, people who do what this person did usually buy item C.
And because the memory is in natural language, prioritize handheld accessories, the LLM can follow that instruction very easily. It doesn't need to interpret some abstract vector score. It just follows the logic.
Okay, let's get into the results. You mentioned they beat the baselines. How significant was the win?
It was pretty consistent. They tested on Amazon Fashion, video games, CDs and vinyl, and the Mind News dataset. They looked at things like NDCG and recall at 10. And AMEM4Rec consistently outperformed AgentCF, LLM Rank, and iAgent.
And who was the toughest competitor in that lineup?
AgentCF is usually the one to beat for this kind of agentic workflow. But AgentCF doesn't have this cross-user memory. It simulates user behavior, but it does it in total isolation.
And the gap was biggest in the cold start experiments.
By far, yeah.
Define the setup there for us. How cold are we talking?
We're talking users with extremely short history sequences, like 2 or 3 interactions total.
Okay, in that scenario, traditional collaborative filtering just falls apart.
It fails because the matrix is too sparse, and standard LLMs fail because there just isn't enough context to infer a real preference.
But AMEM4Rec worked.
It worked because of that shared Borg memory. Even with just 2 items, say Sonic and Just Dance, it can find a similar pattern in the pool. It basically borrows the history of other users to fill in the blanks for the new user.
It's leveraging the crowd to solve the empty profile problem. I want to ask about the ablation studies, because that's where you really see if all this complexity is worth it.
Right.
Did they test if the evolution, the whole rewriting part, actually matters? Could you just store the raw text and call it a day?
They did. They ran a version called Woe Evolution, where they just stored the memories as is, and performance dropped. But the really cool proof was in the TSNE plots.
Right. For anyone listening, TSNE just flattens these high-dimensional vectors onto a 2D map so you can see the clusters.
Exactly. And without evolution, the memory points on the map were just scattered. They were a mess, no clear structure.
But with evolution,
You saw these tight, distinct clusters forming.
so the system was successfully grouping gamers over here, fashionistas there, tech geeks in another corner.
Precisely. The rewriting process actually condenses the information. It pulls similar users closer together in vector space. Without it, you just have a cloud of noise.
What about the semantic validator? That has to be the most expensive part of this pipeline, right? Running an entire LLM just to double-check a match.
It is expensive, for sure.
Could we cut it to save money?
You can, but you shouldn't. They removed it in the ablation study, and performance took a big hit. The analysis showed that without that semantic check, the system suffered from over-evolution.
Meaning it was merging things that shouldn't be merged.
It was just aggregating noise.
Yeah.
It started creating rules based on pure coincidence rather than actual behavioral signals. That validator is the quality control that keeps the memory pool from degrading into, well, garbage.
Speaking of expensive, we have to talk about the engineering reality here. This whole system sounds incredibly heavy.
It is.
You've got a creation agent, a similarity check, a semantic agent, an evolution agent, and a ranking agent. That's a lot of tokens.
It is, and they acknowledge this is a limitation. For the experiments, they used Gemini 2.5 Flash as the backbone.
Why Gemini? Why not something like Llama 3 or Quinn?
They actually compared them, and Gemini 2.5 Flash outperformed Llama 3.8b and Quinn 2.57b. The authors suspect it's because that memory evolution task requires some pretty high-level reasoning. Merging 2 behavioral descriptions into a generalized rule isn't simple summarization. It requires actual logic.
And the smaller open source models just struggle to generate those high-quality archetypes.
Yeah, that seems to be the case.
But the cost to run this for every single user interaction on a platform like Amazon seems prohibitive.
Oh, it's not feasible for real-time high-frequency updates yet. The authors are very clear that the API costs are high.
So in a real-world deployment, you'd have to batch it.
You'd probably batch it, you'd let the user click around, and then run the evolution process overnight to update the global pool.
Or you only run it for high-value users. If I'm buying a $3 ebook, maybe don't bother. If I'm looking at $2,000 cameras, fire up the GPU.
Exactly. And there's also the latency issue. The retrieval and ranking takes time. It's much slower than just a simple dot product search in a standard matrix factorization model.
I also noticed they mentioned the dependence on the embedding model.
Yes, SentenceBERT in this case. If that embedding model doesn't put Sonic Game and Sonic Game sequel close together in vector space to begin with, the whole chain breaks down.
The similarity validator never even triggers.
So the semantic validator never gets a chance to look at it. You're completely bottlenecked by the quality of your initial vectorizer. If your retrieval fails, no amount of fancy agentic reasoning can save you.
So where does this go next? What are the future directions?
They want a move toward reinforcement learning, RL. Right now, the whole system is prompt-based. We tell the agent, hey, rewrite this memory, and we just hope it does a good job.
Right, we don't actually know if the rewritten memory is better until we test it later.
Exactly. With RL, they want to train the memory parameters directly. The system would get a reward signal.
So did this evolved memory actually lead to a click?
Yes. If it did, you reinforce that evolution strategy. If it didn't, you try a different way of rewriting.
That would really close the loop. Instead of us crafting the prompts, the system learns the optimal way to store knowledge on its own.
It would essentially be learning its own compression algorithm for human behavior.
That's a heavy thought. You know, looking at AMEM4Rec, it kind of feels like we're watching the death of the static database.
How do you mean?
Well, for decades, a database was just a place you put things. You put a row in, it sits there. This is a living database. The memories inside are constantly talking to each other, merging, rewriting themselves, and hopefully getting smarter.
It's a big shift from just storage to, well, cognition. The memory pool isn't just retaining facts. It's actively trying to synthesize wisdom.
But it does leave me wondering what the ceiling is here. If you scale this up to millions of users, does the memory pool eventually converge? Does it discover, the universal rules of shopping?
Or does it just keep fracturing? That's the chaos theory part of it. They only tested on sampled data sets because of the cost. We genuinely don't know what happens to the topology of that memory cluster at the scale of a global platform.
It might stabilize, or it might just become a noisy mess without even stricter validators.
It's a fascinating first step, though, moving from people who bought this also bought that to I have analyzed the abstract patterns of 10,000 gamers, and I suggest this specific grip.
It's the difference between statistics and understanding.
Exactly.
Well, we will leave it there. For those of you listening who want to see the specific prompts they used, and they are quite clever, definitely check out the appendix of the paper. We'll link it in the show notes.
Yeah, it's worth a look if you're building agents.
This has been AI Paper Podcasts. Thanks for diving in with us on AMEM4Rec. We'll see you on the next one.